Welcome back to AI.Code.Cast. Today we're diving deep into a problem, and it's a problem that might seem pretty simple at first glance, but it gets really interesting once you start to, explore the algorithmic solutions. It's the flood fill algorithm.
Yeah, it's like, when you're in image editing software and you use that paint bucket tool, you click a point and boom, the whole connected area changes color. But
Right.
I mean, how does that actually happen? What's the magic behind it?
Exactly. And uncovering that magic is why we're here today. So picture this, you have a digital image, right? But think of it as a grid instead of picture a grid where each cell is a pixel with its own specific color.
Okay, I'm picturing it.
So our challenge today is to replace a whole region of these connected pixels, starting from a single point with a brand new color.
It's like we're given a map and a starting point, and a
Yeah,
bucket of paint. And the goal is to color all the land connected to our starting point without spilling any of that paint into the ocean.
I like that. Perfect analogy. So before we get into all the fancy algorithms, a thought just popped into my head, what if we just went through every single pixel in the image one by one, and if it matches the color of our starting pixel, we change it to the new color? Just a simple brute force approach, you know?
Yeah, that's a common first thought for sure. It seems intuitive, right? But there are some pitfalls with that kind of approach.
Oh, really? What kind of pitfalls are we talking about?
Well, first off, imagine a massive image going through each pixel individually would take forever, right? We want an algorithm that's efficient, that's not going to make our computers work too hard.
Okay, efficiency, that makes sense.
Yeah.
But are there any other problems with this brute force method?
Well, think about how pixels are actually connected.
Hmm.
You could end up changing a pixel that, looks like it's part of the same region just because it happens to have the same color, but it might not actually be connected to our starting point. You could even get stuck in an infinite loop, just constantly recoloring the same pixels over and over again.
Oh, I see the issue now. It's like we're trying to paint a continent, but we're randomly dropping paint all over the globe. It's messy and inefficient. As you said earlier, we need a more systematic way to explore these connected pixels, don't we? Something that guarantees we're only coloring the pixels that are truly connected to our starting point.
Exactly. And that's where some really clever graph traversal algorithms come in handy.
Graph traversal.
Hmm.
You're making this sound a little bit more complex now. I thought we were just talking about coloring pixels.
We are, but think about it this way. Our image grid is essentially a graph, right? Each pixel is like a node, and the connections between pixels, they represent the edges of this graph. If two pixels share a side and they have the same color, there's an edge between them.
Okay, I'm starting to see the connection, pun intended. So if we think of our image as a graph, we can use algorithms that are designed to traverse graphs to solve our flood fill problem.
Exactly. And two common algorithms for graph traversal are depth-first search DFS and breadth-first search BFS. These will be our tools for this job.
Okay, this is getting interesting. Let's start with depth-first search. I have a vague idea of what it is, but I'm sure our listeners would love a refresher.
Sure. So think of DFS as like a, meticulous explorer venturing deep into a cave system. They take a path and just keep going as far as possible, marking each cave that they visit before they backtrack and explore other branches.
Okay.
It's all about going deep first.
Okay, so how do we apply this spelunking explorer analogy to our pixel coloring problem?
We can use a recursive function, which is a function that calls itself. We start at our given pixel and check if it's the color we want to change. If it is, we change it to the new color, and then recursively call our function on its 4 neighboring pixels, up, down, left, and right.
So it's like a chain reaction. Each pixel we recolor triggers the same process on its neighbors, and that ensures that the entire connected region gets filled. But how do we stop it from coloring the whole image?
That's where those base cases come in, like the explorer's map and compass, so to speak. Before changing a pixel's color, we need to check if it's within the boundaries of the image and if it has the original color. If not, we stop. It's like our explorer knowing when they've hit a wall or stumbled out of the cave system that they're mapping.
This is all starting to click now. So DFS is like systematically exploring each connected path as dark as possible before moving on to the next one.
Exactly. And the recursive nature of DFS makes it really elegant for this kind of exploration.
Yeah, it is really elegant, but remember I mentioned earlier there's a potential downside to DFS, especially when we're dealing with massive images, something about stack overflows. What was that all about?
Yeah, you did mention that. Can you remind me about that whole stack overflow thing?
Sure, so it all has to do with the call stack.
Yeah.
You see, each time our recursive function calls itself,
Mhm.
it adds a new layer to the call stack, which is like, temporary memory that holds information about the current function call.
If the recursion goes too deep, meaning there are like way too many nested function calls, what can happen is this call stack can overflow, and that causes our program to crash.
So it's like our explorer's backpack is getting too full of supplies,
Yeah.
and it makes it difficult to, maneuver in those tight spaces.
Yeah, that's a great way to put it. And with very large images, the connected regions that we're trying to fill could be quite extensive, right?
Right.
Leading to that deep recursion and potential stack overflow issues.
So what's the solution then if we're dealing with like a giant image and we want to avoid those Stack Overflow headaches?
Well, that's where breadth first search, or BFS, comes in. It's kind of like, instead of plunging deep into a single path, BFS is like a team of search and rescue workers systematically combing a vast landscape.
BFS. So instead of a lone spelunker, we've got a whole team now. I like where this is going.
Exactly. BFS explores our image grid layer by layer, kind of like ripples spreading outwards from, if you drop a pebble in a pond.
Okay, I love that ripple analogy. It's really painting a vivid picture for me. So BFS is all about exploring outward layer by layer, but how do we keep track of all those pixels and make sure we're exploring systematically?
This is where a queue comes in handy. Think
Yeah.
of it like a line at a ticket. Counter pixels get added to the back of the queue and processed one by one from the front, ensuring that, we explore in an orderly way.
So with BFS, we start by adding our starting pixel to this queue.
Exactly, like our search and rescue team marking their starting location on the map, and then as long as there are pixels in the queue, we grab the one at the front and we process it.
So what does processing a pixel entail? In this case, we're still trying to recolor our connected region, right?
Absolutely. We check if the pixel meets our criteria. Is it within the image boundaries? Does it have the color that we're looking to replace?
Right.
If the answer is yes to both, then we change its color to our new color.
Okay, so far so good. We've grabbed a pixel from the queue, we've checked it, we recolored it if needed. What's next?
Now comes the crucial part. We add its neighboring pixels to the back of the queue.
Oh?
Remember, we're exploring layer by layer, so we want to add the pixels directly above, below to the left, and to the right of the pixel we just processed.
It's like our search and rescue team is fanning out to explore the immediate surroundings.
Exactly. And here's the key. By adding those neighbors to the back of the queue, we ensure that we process all the pixels at a given distance from our starting point before moving on to pixels further away.
Uh-huh. So we're systematically exploring outward in those ripple-like layers. We handle all the immediate neighbors first, then their neighbors, and so on. It's like a perfectly organized search party.
You got it.
Yeah.
That's the beauty of BFS. We repeat this process. Grab a pixel from the front of the queue, check it recolor if needed, and add its neighbors to the back.
Okay.
This continues until our queue is empty, meaning we've explored and potentially recolored all the connected pixels of the original color.
This is fantastic.
Yeah.
DFS sounds like a really robust way to handle flood fill,
Yeah.
especially for those massive images where DFS might run into trouble with stack overflows.
It usually is by using a queue instead of recursion. We avoid those deep nested function calls and, keep our program happy and healthy.
Okay, so we've now seen two different approaches to solving the flood fill problem. DFS, our intrepid spelunker going deep, and BFS, our organized search and rescue team, methodically exploring layer by layer, both fascinating in their own right. But the question that's probably on everyone's mind is which one is better?
The age-old question. And as with most things in computer science, the answer is it depends. Each approach has its own, strengths and weaknesses.
It's not a simple DFS always wins or
Mhm.
BFS is the only way kind of situation.
Not at all. DFS, with its recursive nature, is often more concise and easier to understand, especially for people just starting out with graph algorithms. But that reliance on the call stack can be its Achilles heel when you're working with really big images.
So BFS being iterative and using a queue is generally the more robust choice for those massive images because we don't have to worry about those pesky Stack Overflow errors.
Exactly. It gracefully handles large data sets, but sometimes setting up that iterative logic with the queue can feel a bit more involved compared to, the elegance of recursion.
So it's a trade-off then between simplicity and robustness, like choosing the right tool for the job.
Precisely. And understanding those trade-offs is key to making informed decisions when you're designing algorithms.
Speaking of informed decisions, you mentioned that both DFS and BFS have a time complexity of O of m times n, where m and n are the dimensions of our image. What exactly does that mean in plain English?
It means that in the worst-case scenario, we might have to visit every single pixel in the image. The time it takes to run our flood fill algorithm will grow proportionally to the size of the image.
Okay, so a larger image means potentially more pixels to check and recolor, which could take longer to process. Makes sense. And what about space complexity? How much memory do these algorithms need to do their thing.
The space complexity is also O of m times n in the worst case, both for DFS and BFS for DFS. This comes from the potential depth of the recursion. Remember, each recursive call adds a layer to that call stack for BFS. It comes from the potential size of the queue, which can grow quite large depending on the shape of the region we're filling.
So they might approach the problem differently, but when it comes to efficiency, both DFS and BFS are in the same ballpark, at least in terms of big O notation.
That's right. The choice between the two often boils down to those practical considerations we talked about: the size of the image, the potential for stack overflow, and even personal preference or coding style.
Earlier you mentioned that we can think of an image grid as a graph. This makes me wonder if DFS and BFS are limited to just image processing. Are there other scenarios where these algorithms come in handy?
That's a great question. DFS and BFS are fundamental graph traversal algorithms with a wide range of applications beyond just images.
Like what? Can you give some examples?
Imagine you're designing a maze-solving algorithm. Both DFS and BFS could help you find a path from the entrance to the exit.
Or what about navigating a complex network like social media connections?
Absolutely. These algorithms are essential for tasks like finding the shortest path between two people in a social network or mapping out the connections between web pages.
So understanding DFS and BFS unlocks a whole toolkit for solving problems that involve connections and relationships, not just pixels on a screen.
Precisely. They're foundational tools for exploring and understanding complex structures, making them incredibly valuable in computer science and beyond.
Well, this has been a really enlightening deep dive into the world of the flood fill algorithm. We've gone from the simple act of clicking a paint bucket tool to uncovering the fascinating world of graph traversal algorithms like depth-first search and breadth-first search.
And we've seen how these seemingly abstract concepts have very real and practical applications in everything from image editing to maze solving to navigating complex networks.
To our listeners out there, we encourage you to explore further experiment with different implementations of flood fill. Try visualizing the steps of DFS and BFS, and maybe even brainstorm your own hybrid approaches.
Remember, understanding these fundamental algorithms opens up a world of possibilities. Who knows, you might even come up with a new and improved way to fill those digital buckets of paint.
Thanks for joining us on this deep dive into the flood fill algorithm. Until next time, happy coding.